Okay, here we go. Today is September 24th. Today we are talking about composition of functions some more today. But our focus today is talking about domain. And the domain for composition of functions is quite a challenge. So we want to make sure that we understand that piece fairly decently. I guess it's a start of an understanding. It's quite complicated. All right, first of all, we have this g of f, g over f of x. What does that really mean? G of x divided by f of x. So it's easy to do. Our g function is x plus 5. And our f of x function is x squared minus 4. And this is a lovely answer, but what might we be able to do with the denominator? Factor. So we can factor. And you don't have to. But I love when denominators are factored because we can see the domain really, really easily. What is the domain of this g over f function? X cannot equal plus or minus 2. Why? Yeah, denominators cannot equal 0. And that's one of our domain things that we look out for. Denominators are not allowed to be 0. So negative 2, if I plug that in, negative 2 plus 2 is 0. That makes us divide by 0. It's undefined, not allowed. Here, if we plug in a positive 2, makes, again, the denominator 0 and the function undefined. So that's one of our special rules. What's another special rule for domain we have?
There could be square roots.
Well, that's true. But tell me about square roots. Tell me about square roots. They can't be negative. They can't be negative. They must be greater than or equal to 0. Why can't square roots and fourth roots be less than 0? They're imaginary. That's right. So we need them to be greater than or equal to 0. So these are our two things that we have to look out for in terms of domain. Otherwise, most things have a domain of all real numbers or negative infinity to positive infinity. So everything else you can look at the graph of. In fact, you can look at the graph of all of them to see the domain, okay? But usually, most of the time, the domain is all real numbers. There's a lot more things we have to look out for in terms of domain. These are just the first two, okay? So we'll learn a lot more.
So boring.
All right, so example 1. Example 1, find the following. Given f of x equals 1 over x and g of x equals x over x plus 1. And also find the domain of each. All right, we have fg of x here. What does fg of x really mean?
F of x times g of x.
Good, f of x times g of x. And, well, that's pretty easy to do. I can replace f of x with 1 over x. And then I can replace g of x with x over x plus 1. Now, we've done this before. This is multiplying fractions, which means we can do some simplifying if we can. How do we multiply fractions? Straight across, right? Okay. But before we do any simplifying, we need to think about the domain. Looking right here, before I simplify, tell me what x is not allowed to be.
0.
Good. X is not allowed to be 0, and it's not allowed to be -1. It's really important that we find that domain before we simplify. Because what's going to happen when we simplify? Yeah, the x on top and x on bottom reduce, and we're left with 1 over x plus 1, which is a lovely answer. But when you just look at the domain of that final answer, what does it say? X can't be -1, which means we're missing part of the exclusions, okay? And so it's really important to think about domain. Think about domain before you simplify. All right? Really important. All right, what does f over g of x really mean? F of x divided by g of x. And of course, we can do that. F of x is 1 over x divided by g of x, which is x over x plus 1. What did we just create here? Complex fraction. Complex fraction. So we have a fraction divided by a fraction. What are we going to do about this? Keep, change, flip. So we are going to, instead of dividing by a fraction, we're going to multiply by the reciprocal. So what am I going to multiply by? X plus 1 over x. Very good. And again, we're multiplying fractions. We just multiply straight across. Does this one clean up much? No, it doesn't. We get x plus 1 over... Something is funny. It's really annoying. All right. What's the domain of this?
X.
X cannot equal 0. Okay. Now the question is, do you think that's it? No. Okay. And this, I want to illustrate this because it's really important. We don't just look at the answer and say the domain is x can't equal 0, because we simplify. We simplified right here by doing the keep, change, flip. That's a simplification. And so we actually need to go to right here before we simplify and take a second and think about all of the denominators. How many denominators do you see?
3.
3 is the right answer, sir. Good job. 3 denominators. There are 3. You ever see those those little puzzles where they're like, it's just a whole bunch of like squares? How many squares in the picture?
Yes.
Yeah.
I hate
those, right? This is the same thing. All right. So first of all, there's a denominator. So looking at that denominator, what is x not allowed to be?
0.
Okay. Oh, and then there's a denominator. So looking at that denominator, what is x not allowed to be?
1.
Okay. And then there's one more. Where's the third denominator? The whole denominator is another denominator. X over x plus 1 is not allowed to be 0. How do you solve that? Multiply by x plus 1. So multiply the x plus 1 to the other side. What is 0 times x plus 1? 0. Oh, so we get another x cannot equal 0, which we already had. We didn't need it twice. But that's something you should think about. This is an incomplete domain. We also want to make sure that x is not allowed to be that -1. Okay? So that's just to illustrate what happens when we simplify. So you have to be super duper careful.
So, would you put that in the
No, so you'd solve this? Yeah, so we would solve. This is an equation we can solve. So I multiplied by the x plus 1. 0 times x plus 1 is 0. Yeah, so if it was x plus 7, then we'd have x plus 7 cannot equal 0, and you'd move the 7.
Okay.
Yeah. All right, so please be careful with domain, and always do domain. Think about domain before you simplify, okay? All right. Those were the easy ones. Are you ready?
No, I'm hiring. So let's just not do this.
All right, here we go. Example 2. Find the domain of each and the domain of the composition, and find the composition. Not necessarily in that order. Find the domain of each, which is asking you to find the domain of F and find the domain of G. Then we want to find this composition, which, look, it's printed correctly. That's how it should look. I don't know what it was doing yesterday. That's what it should look like. So we're going to do the composition, and then we're going to find the domain of the composition, which is really difficult. Mrs. Linton is agreeing with me. Yeah, good luck. There's a printer back there.
Yeah.
Yeah, that's this end of the hallway.
Printy winty.
Okay, we have f of x equals x squared plus 2, which looks a little funny because I wrote that in my hand. I changed the problem. I maybe shouldn't have in hindsight, but it's good. Too late now, yeah. And then g of x equals the square root of x. So the first thing I want to do is find the domain of each. So I want to find the domain. I'm going to start here with this g of x function, finding the domain of the g function. Tell me about this g function and domain. Well, that's for denominators. What does this one have to be? Can't be negative. That's right. So that square root of x must be greater than or equal to 0. If it had other things added or subtracted, if it was like the square root of x plus 9, all we care about is the radical. The 9 makes no difference. This is still the thing that we would say you have to be greater than or equal to 2. Okay? Wait, we're not on that one. So I want to solve this little equation. How do you get rid of the radical? Square both sides. And so you'd have x is greater than or equal to 0. This is the domain for the first g of x function. And then let's see, over here, I'm going to do the domain for the f of x function. Tell me about the f of x function. What do we need to pay attention to? The denominator. Tell me about denominators. They can't equal 0. The entire denominator, x squared plus 2, cannot equal 0. All right, how do we solve that equation? Subtract 2, so x squared cannot equal negative 2. And take the square root. All right. What happens when I try to take the square root of this? Oh, it's imaginary. Okay. And this is why I wanted to do something like this. We haven't seen a domain that turns up like this. I haven't taught it. It might have appeared in your homework, but I haven't taught it necessarily. What that means is there aren't any real values that I need to exclude. They're imaginary. They aren't really there, which means everything works. All right? Because it's imaginary, this domain is negative infinity to positive infinity, and I'm going to show you. When in doubt, graph it out. So if you're ever wondering, hey, what what is the domain? You can always look graphically. So you can see I put my function into my calculator. I made sure that I put parentheses around that denominator. And you'll notice when I go to graph this, it looks like a little blip in the screen. I'm going to change my window because it's really tiny. I want my y-axis to just go from -1 to +1. And now you can see, look, it's a little hill. Oh, cool. All right. But how far left and how far right does it go? Forever, right? And that is the domain from -infinity to +infinity. Okay. So when in doubt, graph it out. You can always look at the domain. Okay. So here, there was nothing real to exclude. It turned out to be imaginary. So now we need to find the composition. So we need to find, what does f of g really mean? F of, and then on the inside, we have g of x. Okay. I can do that. What can I plug in place of g of x? Radical x, okay. And so now I have f of radical x. What does f of radical x tell me to do? Plug in radical x in my f function there. So I can do that. 1 over something squared plus 2. And what goes in place of the x? Radical x. Very good. All right. Well, that's interesting looking. That is 1 over, what is radical x quantity squared? X. Good. Okay. This is f of g. This is the composition. Now the hard part. We need to actually find the domain of a composition. So write this down. The domain of a composition is the domain of the inside function and the result. So there are 2 pieces to domain, and we have to compare 2 different pieces. So the first thing we have to compare is the domain of the inside function. What do you think I mean by that? Where's the inside function? Oh, right here, the g of x, this, the radical x, that is the inside function. The one that we're plugging in. Okay, so I'm going to look at the domain of the inside function, and I'm going to actually just graph it. My inside function was my g of x function, and I know the domain. What was the domain of my g of x function? Yeah, right here. Right here, this is my domain of my g of x function. X had to be greater than or equal to 0. So there's 0, and I'm going to put a big solid dot there at 0, and I'm going to shade to the right. My green pen is dead. Okay. It's very sad when your pen's dead. All right. And then I need to look at the domain of the result. Where's my result? Right here. This is my result. Looking at my resulting function, tell me about this resulting function. X cannot equal -2. So here's my result. I am going to graph that result. So right here is -2. -2 does not work, but everything else does, right? So everything to the right works, and everything to the left works, but -2 does not work. The domain of f of g is what works for both of these. What works for both? Does -infinity to -2 work? No. Okay. So, but starting here at 0, they both work at 0, and everything to the right. So from 0 all the way to infinity, that is the domain of f of g. Isn't that interesting?
Yes.
Okay? It's not the domain of the result, is it? This is the domain of f of g. Okay? The bracket at 0, because does 0 work for the first one? Does it work for the second one?
Yeah.
So it works for both, so we include it. All right, ladies and gentlemen. Oh, we have one more. Oh, yeah. One more. This is a fun one. And in case you're curious, number 41 is on the board of your homework.
Yes!
Oh.
One less problem.
All right, here we go. This is example 3, not 4, because I can't count. Hey, I've never professed to be good at math.
Yeah, you just have to cross like a doctor.
I mean, that's why it's called practicing medicine.
All right, I'm gonna give you. No, I'm not gonna give you a minute. I just want to get this done. Okay. We're gonna use the graphs. You can watch it again and pause as necessary. So here we go. Use the graphs to find the following. So I would say just pay attention, and then you can copy it down after the fact. So I have here, we have the graph of the f function, generic f function, and here we have generic g function. And I want to find f plus g of 1. And again, the key to all of this notation is actually understanding really what it means. What does f plus g of 1 really mean? F of 1 plus g of 1 is what that really means. And now we can look at our f function. What is f at 1? 2, yeah. Remember, function notation is simply an ordered pair where we have an input of 1 and it's asking, God bless you, what is the output? The output is 2. What is g at 1? Also 2. All right, at 1, we have an output of 2, and 2 plus 2 is 4. Okay. What does f over g of negative 3 really mean? F of negative 3 over g of negative 3. And what is f at negative 3? It's actually 3. So negative 3 is 3. So the output is 3. And what is g at negative 3? 2. Negative 3, and it has an output of 2. So it's 2. And there you go. 3 over 2. What does g over f of negative 1 really mean? G of negative 1 over f of negative 1. Very good. What is g at negative 1? 1. It's this point right here. Negative 1, 1. And what's f at negative 1? 0. Yes. What does this really mean? Undefined. When the 0 is under, it's undefined. Okay. Last one. F of g of 4 really means what? I know. F of g of 4. So we need to start on the inside of the function. What is g of 4? 1 right there, 4, 1. So that has an output of 1. So then we're really, now we have to find, well, what's f of 1? 2. Okay. questions for me? Alright, cool. You guys can work on your home.